Hello, I'm Obelia, and today I'm going to share a topic about dirty rectangle rendering. First, a little information about myself. I'm the VP of Apache ECharts, and I joined the project in 2016. I believe in the power of data visualization, and experience with ECharts makes me more sure of that. First, let's have a basic idea of the background of the topic. Why did we introduce dirty rectangle rendering in ECharts? As we know, one of the highlights of ECharts is its ability to render big data. For scatter charts, ECharts can render 10 million data points in real time with interaction. And for a heat map like this, with tens of thousands of data points, before any kind of performance optimization, we will find that the interaction is not very smooth, where frame rate is around a dozen FPS. If we look closely, we will find that only a small part of the chart is changing, the highlighted area where the mouse was and is hovering. Therefore, the problem we want to solve is a specific scenario in which the majority of the elements in the frame do not change, but only a small part. How to optimize the rendering performance in such a scenario is the focus of our discussion today. Here is the rendering framework of ECharts and its underlying rendering engine, ECrender. All types of charts and components are composed of elements like rectangles, lines, and paths. In ECrender, we have a rendering proxy to draw those shapes, so that when defining a shape, we do not have to consider it's implemented with Canvas or SVG or even other rendering engines. Today we will focus on Canvas rendering. The basic workflow with Canvas rendering is in each frame, you clear all the canvas and render new elements onto it. But a canvas with a large number of elements, like 40,000 rectangles in this example, is time-consuming to re-render all 40,000 data in a single frame. And this is exactly the reason why the animation does not seem to be very smooth enough in this case. Let's take a simpler example to understand the situation here. Is it possible if we only render the changed elements in the canvas? Well, in this simple case, yes. And this method is called hovering layer, and it is supported date back to ECharts 4. The basic idea of a hover layer is to use an extra canvas on the main canvas to render the elements modified because of mouse hovering. Since we do not need to re-render all the elements in the chart, this solution can improve rendering efficiency a lot. But its disadvantages are also worth considering. First, it has extra memory cost since it uses an extra canvas. If there are many charts using hovering layers in the same page, or it's on a low-cost mobile device, it may cause noticeable efficiency problems. Second, there are platforms that do not support multiple canvases, like WeChat Mini Program. In these platforms, we cannot use an extra canvas for the hover layer. Third, since the original element is not cleared in the main canvas, it may cause rendering bugs if the modified elements are translucent, in which case we can still see the old elements beneath. Last but not least, since the hover layer is displayed on top of the main canvas, all elements rendered in the hover layer are on top of the elements in the main canvas. So the hover layer solution can only be used to render the elements at top, which is exactly it's called a hover layer. That being said, is it possible to render modified elements only? Yes, and this is why we introduced dirty rectangle rendering. But to render the modified elements only is not as easy as it seems to be. Canvas contains pixel information only, meaning that you cannot clear the modified elements only, but a certain shape of area, like a rectangle. So we could calculate the bounding box of the modified shapes and repaint those areas. But we still need to repaint other shapes that have intersection with the bounding box, as they have been partly cleared also. So to calculate the repaint areas, we first calculate the bounding box of each modified shapes, and then merge boxes if they intersect with each other. After that, if the merged rectangles are more than 5, we further merge them until the merged number is less than or equal to 5. We calculate the reduced area of each pair and find the least pair to merge them. The reason why we need to merge the bounding boxes and to restrict the number to be small enough is that it is possible that in a bad case there are hundreds of thousands of elements modified in a single frame. For each of the bounding box, we need to loop through all the elements in the scene to check intersection and paint if intersects. So by restricting the number of bounding boxes, we make sure that in a bad case, the overall performance could not be too bad. After calculating the merged area, we now loop through all the elements in the scene and check if they intersect with the merged area. If so, we repaint the element and do a clipping at the merged area. In this example, the color of the triangle changes and the repaint area is the bounding box of the triangle. The circle is intersected by the repaint area, so the elements that need to be repainted are the triangle and the circle. One thing to note that is when repainting the elements, we need to clip the element within the repaint area to ensure that only the elements within the area are rejoined. For example, the circle can only be drawn in the upper right corner, otherwise it is translucent. The outside part will be drawn twice and have a darker color than expected. Next, let's go through the source code to understand that detailed part of the process introduced above. First of all, the bounding box is calculated. Since the elements may have been rotated, scaled, and translated in the scene, we need to do the same transformation for the bounding box to get its word position. Then we need to add the size of the shadow because the shadow is not transformed in the canvas. You need to add it after the result of the transformation. This is the position of each element in the current frame. If an element is marked dirty in the current frame, which means that the position or color or other properties of the element have changed, then its bounding box should be added to the repaint area. We also need to hold the bounding box of the last frame, because we need to include both the bounding boxes of the current frame and the last frame. When repaint, we need to check if the last frame exists, and if the elements have been modified or deleted, then the bounding box should be added as well. This is the result of dirty rectangle rendering with Apache ECharts, in which the red rectangles are the repaint areas in each frame. We can see that only a small part of the chart is being repainted in most cases. In addition, some browsers like Chrome refreshes only at the modified areas, giving us extra bonus for the rendering performance. The green part of the figure shows the refresh positions at the browser level. This is a real-world example of Apache ECharts tree map. Without dirty rectangle rendering, the FPS is about 10. The red color in the bottom bar indicates the interaction blocking time. After enabling dirty rectangle rendering, we can see that the FPS has been increased to 60 and the red blocking time has been significantly reduced. In conclusion, using dirty rectangle rendering can be an effective solution for scenes with a small area changing. There is no extra canvas layer, so there is no extra memory cost. And it is also a more general and correct way to do it, and do not have the problem of translucent elements. The disadvantage is that for scenes set where most of the elements are changing frequently, there is more extra overhead due mainly to the loop-over elements. Therefore, dirty rectangle rendering is disabled by default in ECharts, and it can be enabled when developers find it necessary. That's all for my today's speech. If you have any question, welcome to ask me now or send me an email. Thank you.